What is going on, guys? Welcome back. In this video today we're going to learn about genetic algorithms and how to implement them in Python. So let us get right into it. Alright, so we're going to learn about genetic algorithms in this video today, and we're also going to learn how to implement them in Python. Now, genetic algorithms are so-called meta-heuristics that are used to solve optimization problems using an evolutionary approach. So when you have an optimization problem, instead of solving it with an algorithm or a heuristic or an approximation algorithm or even with machine learning, we use an evolutionary approach to find good solutions. That's the idea behind genetic algorithms. And to not keep this too abstract here, I'm going to give you an example right away. We're going to use a very, very simplistic and trivial example just to illustrate the concept, and this concept can then be applied to real problems or specific use cases. So let's say I have this scenario here. I have a list, and in this list I have a couple of slots, and I can have some values in here. And let's say that the values that I can have in the list are either 0 or 1. So I can have something like this. This would be a valid solution to the optimization problem. And let's say that what I'm trying to optimize for is the maximum number of ones. Now, again, this is very trivial and very simplistic just to illustrate the example. So my goal is to get only ones, or to maximize the number of ones in this list. Now, of course, since this is a very trivial example, the easiest way to do that is to just set all of them to 1. But you can imagine this to be something else, like, for example, the set cover problem. The set cover problem is you have a universe of values, so something like 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, and then you have different sets. One set could be 1, 3, another set could be 4, 5, 8, another one could be 1, 8, another one could be I don't know, 1, 7, 8, something like this. And you have all the different sets so that some combination ends up representing or ends up covering the whole universe. So imagine you have a bunch of more sets here, and in certain combinations you can get all the numbers from the universe here. This is the set cover problem. The question here would be, if this is now a more real problem, is which sets should I pick to cover the whole universe while keeping the number of sets used to a minimum. So for example, if I have another set here, let's say I have the set 2, 4, 5, 6, 7, 8, 9, then I can cover the whole universe with 1, 3, and with 2, 4, 5, 6, 7, 8, 9. So with 2 sets, I can cover the whole universe. Of course, I can do the same thing with other sets. So maybe I have a set here with just 1. And maybe I have one with just 3, so that would also be a valid solution to the set cover problem, but it uses 3 sets instead of 2 sets. So this is a real optimization problem where you try to keep the number of sets low while covering the whole universe. This here is a very simplistic example, just to illustrate the concept. So I just gave you this so that's not just a random trivial example, but you have some real use case for this genetic algorithm stuff. Now, this problem that we're looking at up here is called the 1-max problem. It's considered to be the hello world problem for genetic algorithms because it's so simple. And of course, it doesn't make sense for this problem to use genetic algorithms because all you have to do is you just have to get the length of the list and fill it up with ones. That's all you have to do. But how does a genetic algorithm solve this problem? Or how does a genetic algorithm find solutions to this problem? There are basically 3 parts to that. One is that you have a representation, and this representation, or actually that's not a part. The representation is what you need, and then you can do certain operations. You have the 3 operations, which are reproduction, mutation, and selection. These are the 3 important pieces of a genetic algorithm, because what you do is you have a population of different solutions. So this could be one solution. Then you could have another one which looks something like this, maybe. I don't know. That could also be one. And they have different fitness values, you could say. Now, a fitness value is just saying how good is this solution. In the case of the 1-max problem, this fitness value, of course, is very simple, the sum of the numbers, or the amount of ones in a list. So in this case, the fitness of this solution here would be 4 because we have 4 ones in it, and the fitness for this one would be 7 because we have 7 ones in it. In the case of the set cover problem, for example, you might want to use the number of sets used as a fitness function if you want to only allow for solutions that cover the whole universe. Otherwise, maybe you can also include somehow into the formula for the fitness how much percent of the universe is covered using the solution. So it's important to come up with some fitness function. In the case of a 1max problem, very simple, just count the number of ones, that's your fitness value. Now, the next thing is you need to reproduce. So you need to somehow combine solutions because remember, we're talking about an evolutionary algorithm here. We want to take two solutions and combine them. We want to make them reproduce. So how could we make these two reproduce? Now, there are different ways to do that. You could just take individual bits from the individual solutions at random, or you can do something like a crossover, for example. A crossover is you choose some index. So for example, I can say this is the position I want to do the crossover on. So I can put a colon here. And then what I do is to combine the two solutions to a new solution. I take the first part of the first solution, so 0, 0, 1, and then I fill up the rest with the second part of the second solution, so 0, 1, 1, 1, 1, 1, 0. And that then would have, in this case, also a fitness of 7, but it could improve, it could become worse. And then what you also want to do is you want to have a mechanism for mutation. A mutation, in this case, could basically just be saying flip bits at random. So, for example, we might want to flip this bit. And then, you know, with a certain chance, we're going to have some mutations. In this case, if that's the only mutation, it would lead to a fitness score of 8. So this is the basic idea on how you can approach good solutions. Now, how do the solutions get better overall? By using a selection method that makes sense. For example, picking just the best solutions, or using something like a roulette wheel selection, or there are different ways to decide which of the instances you want to keep, because the worst instances are going to not survive. They're not going to make it to the next generation. That is now a very rough description of how genetic algorithms work. Now we're going to implement this here with core Python. We're not going to use any packages. We're going to implement the 1max problem so that you can see how it works. And then you can invest some thought on your own. And I can also make additional videos on this, how to apply this to actual problems. So let's start and say we want to import random. And then let's go ahead and define some constants here. Let's say we want to have a population size. The population size can be 100, which means that we start with 100 solutions. They can be random. You can initialize them intelligently if you want to. You just get some solutions. Initially, you have a population size of 100. Then we want to have a genome length. Now, a genome length is just the length of the individual solutions. Let's say 20. So this would mean that we have 20 positions to fill up here. So this 20 times. So 20 zeros or ones. Then what we want to have is a mutation rate. So remember, we said a mutation could be flipping a bit. What is the probability of a mutation happening? Let's say in our case, it's going to be 1%, 0, 0, 1. And then we're going to also have a crossover rate. And the crossover rate is just going to say how likely is it that we're going to do a crossover instead of just returning the parents. So if I select parents P1 and P2, there's a chance that I'm going to just return them without any mating, without any reproduction, or I'm going to do the crossover. And we want to have a 70% crossover rate here. Of course, you can tweak these values if you want to. And then the last parameter here is going to be the generations. I want to do 200 generations, which means that the whole process is going to be repeated 200 times. Now, what we're now going to do is we're going to define a function called random genome. Now, you don't need to make this a function if you don't want to. I just like to have it in functions here in a modular way. This is going to just return a random genome. No reproduction, no mutation, just a random genome as an initialization. It's going to accept the length argument, and it's going to return random integer between 0 and 1 for placeholder in range length. So just a random list of zeros and ones with the length that is passed here. And this length is, of course, going to be our genome length. Then we also want to have an initialized population function. So we're going to have init population and the population is going to take the parameters population size and genome length. And of course, feel free to combine these functions or to not have functions at all, to just write down the code if you want to. I just want to keep it structured here. Let's say now we're going to say, what we want to do is we want to return a random genome, or we want to return population size number of genomes. So we want to say random genome with genome length 4 underscore in range population size. So basically here we're generating bits, here we're generating actual genomes, and then we have our initial population, which is going to be initialized randomly. So it's not going to have any intelligence already in it. It's just going to be random zeros and ones. Then as our fitness function, this is very simple. We get a genome, and the fitness of this genome is just going to be the sum of the genome. Now, if you have multiple values, if you don't just have 0 and 1, if you have 2, 3, 4 or something, maybe you want to count the number of ones if you want to still optimize for the number of ones. But in this case, counting the number of ones and taking the sum is the same. So we want to return the sum value here as our fitness. And then we get now to some more interesting stuff. Selecting the parent. Now, let's define a function, select parent. And this function takes the population, the full population, and the fitness values. So the fitnesses, we could say. Well, let's call it fitness values. Sounds more professional. So we have the population and the fitness values, and we can say total fitness is the sum of the fitnesses, or of the fitness values. So we get the total amount of fitness that is available here. And then we're going to say we want to randomly pick a fitness value here as a reference point. So we can say, and of course you can use a different selection algorithm if you want to. But what I'm going to do here is I'm going to say random uniform. I want to take something in between 0 and the maximum or the total fitness value that we have here. So what we're going to do then is we're going to say current equals 0, and we're going to start a loop for each individual in the population and for the corresponding fitness value. So actually fitness, let's call it value, fitness value in. We're going to zip the population and the fitness values so that we can iterate over both. We're going to increase the current by the fitness score, or by the fitness value that we have here. And if this current value becomes larger than the pick, than the random pick that we made up here, then we're just going to return this parent as the individual, or this individual as the parent. This is one selection mechanism. It's basically a random selection. We want to have some random pick here, and once we get to the value that was picked here, by adding up the fitness values, we're just going to return that parent here. So this is just a function for selecting the parent. Now, where it gets interesting is crossover and mutation. Now, crossover, as I explained, is our reproduction method here. It means we take two parents and we pick a point, and then we take the first half of one parent and the second half of the other parent. So we can call this either a crossover or a reproduction method, whatever you want to call it. And this just takes parent 1 and parent 2. So we have our crossover rate, which means that we're not going to just always do the crossover. We're going to say if random dot random, if that is less than the mutation rate, then we're going to return the crossovers. Otherwise, we're going to just return the parents. So we're going to do a pass here. If it's not less than the mutation rate, we're going to return just parent 1 and parent 2. In the case that it is actually less than the mutation rate, we're going to return parent 1, and we're going to pick a point. So we're going to say here that the crossover point, maybe let's call this crossover point, not point, is going to be equal to some random point, some random integer between 1 and the length of the parents. So the parent 1 length is going to be the same as the parent 2 length, but we don't want to pass here again the genome length, so we can just get it from here. So this just gives us some point, some random point that we can choose, and then we're going to return parent 1 up until this point plus parent 2 from this point onwards to the end. And the same thing, I need to call this crossover point, not just point. Crossover point, there you go. And the other way around, we're going to return parent up until this crossover point, parent 2 up until this crossover point, plus parent 1 up until this crossover point. Or actually, crossover point until the end. So we're just using both here as a return value. We're returning both. Then we also want to implement the mutation. The mutation in our case is going to be just flipping a bit. So we're going to say mutate the genome. Do we want to mutate the genome? For I in range length of the genome. So for each bit, we're going to say if random is less than mutation rate. So for each bit, there's a 1% chance we're going to flip it. And what we do here is we basically say, okay, if this chance happens, we want to flip a bit. So we're going to say the genome that the bit that we're currently looking at is going to be 1 if it was 0 before. So if genome I is equal to 0, otherwise it's going to be 0. So we're just going to, actually, isn't there a mathematical way to do it? Could I not just say, I think I can make this in a more intelligent way. I can say 1 minus genome I, because I think 1 minus 1 is 0 and 1 minus 0, no, actually doesn't make a lot of sense. Wasn't it like the absolute value? I want to figure this out now. I can do the absolute value of genome minus 1. Shouldn't this work? If it's 0, it's going to be 1, because 0 minus 1 is negative 1. And if it's 1 minus 1, it's going to be 0. Okay, I think this should work. I hope so. And then we can return, in the end, the genome once we're done with all the mutations. All right, so that is what we need now to implement our big function, the genetic algorithm itself. So the genetic algorithm is going to be the following function. It doesn't take parameters because it's just going to use them from up here. We're going to do now population is going to be equal to initialize a population with the population size that we defined as a constant and the genome length that we also defined as a constant. And now we're just going to go through generations of doing the process of the genetic algorithm. So for generation in range generations, we're going to calculate all the fitness values. So fitness values is going to be equal to fitness of the genome for genome in population. So for each genome in a population, we're calculating the fitness score, we're keeping track of them in a list, and then we're defining a new population, or you could also say the population of the next generation. And the new population will start as an empty list. And we're going to say for placeholder in range population size divided by 2, because we always take 2 parents, so we don't need to do it for the full population size, but only for half of the population size. So we floor divide by 2. We select 2 parents, so parent 1 is going to be equal to select parent from the population with the fitness values that we have here, and parent 2 is going to be the same thing. So we're just selecting 2 parents, and then we get the offspring. So we get the future genome. It's either going to be the 2 parents themselves, or it's going to be the crossover result. So offspring 1, offspring 2 is going to be equal to crossover parent 1, parent 2. And then we're going to extend our new population. We're going to extend our new population by our offsprings. And of course, we also need to mutate them before. So we need to say mutate offspring 1 and mutate offspring 2. So maybe we're going to flip some bits. And then basically what we do is we get the population again. So we say population is equal to new population, because otherwise when we talk about the population here, it's always going to take the initial one. So we need to update this to the new population. And then we want to, again, get all the fitness values. So the fitness values are going to be, actually, let me just copy this. It's going to be these values here, and we're going to say that the best fitness we have is max of fitness values. And we can print that here as a status message. We can say generation, and then generation, best fitness is equal to best fitness, just so we can keep track of that. And in the end, what we want to do after the for loop is we want to say that the best index is going to be the index of the best fitness value. So fitnesses or fitness values index max fitness values. And then what's the problem here? Fitness values might be referenced before assignment. No, it won't be, because generations is not going to be 0. So best solution is then going to be the population instance, so the individual, the genome that has this index in the fitness values list. So we can then print best solution, and then we can say the best solution is equal to the best solution, and the best fitness is going to be the fitness value of this best solution genome. So in this case, I'm calculating it again. Of course, I could also take it just from the fitness values list, but that's fine. And then finally, what we want to do is we want to say if underscore underscore name underscore underscore is equal to underscore underscore main underscore underscore, then we're going to run the genetic algorithm. That is it. I'm going to explain it here in a second again. What's the problem up here? I saw some stuff not... What is this? Did I mess up something with the formatting here? Initial population. No, okay. I just have to remove this. Okay. So now I can run this, and what you see is that something doesn't seem right here. Let me just double check. Oh, I think I figured out what the problem is. We have our crossover here, and we're checking if it's less than the mutation rate. We should check if it's less than the crossover rate. Otherwise, we're not going to have any reproductions, almost. So let's run this again. And there you go. Now I actually increased the number to 2000 generations. So here, after 200 generations, you can see it found the optimal solution only once. And I can run this a couple of times. Maybe sometimes it's only going to get to 19 or 18, but you can see it improves over time because it starts with a 17 here. Now we can also increase the genome length. So we can say we want to have 50 genomes. And in that case, the progress is going to be slower. But if I increase then again the the generations, probably, no, it doesn't even get to the best solution in this case. So maybe if we increase the mutation rate, no, seems even worse. Maybe if we reduce the crossover rate, or if we do both, you can play around with that. So it doesn't seem to make a lot of sense here in this case. But this is just the hello world example of genetic algorithms. So to go back to the beginning, what you actually want to do is you want to take a problem, an optimization problem. Good examples for this are, as I said, the set cover problem, graph coloring, or traveling salesman problem, TSP, or basically any problem that you can somehow, any optimization problem that you can somehow represent here as a genome. Also the knapsack problem, stuff like this, because all you have to do is you have to think about how are you going to represent your genome. What is your genome going to be? And then you also need to come up with an idea for the fitness function. So for example, as I said, you might have the individual sets. Which ones are you going to choose? I choose set 1, I don't choose set 2, I choose set 3, I don't choose set 4, I don't choose set 5, but I choose set 6. And that covers the whole universe. So we only have 3 sets here. The fitness could be you know, in this case, the number of possible sets used minus the number of actual sets used. So you could have, in this case, if it's 6 minus 3, it would be 3. If it's like this, it would be 2. Because I'm using 4 sets and you want to minimize the number of sets. Or for graph coloring, maybe you want to have each index represents a node in the graph, and then the value of that index or of that position says which color we're using. So it could be something like 1, 2, 1, 2, 2, 2, 3, 1, 1, 1. In this case, the fitness would be 3 because we used 3 colors for the graph. And in the graph coloring problem, you want to minimize the number of colors used. So that's just another idea here. So yeah, this is how you can work with genetic algorithms in Python. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.